Okay, the next part of this forecasting module is a discussion of fronts. You actually have two questions in terms of fronts. Actually, three questions. The first one is a frontal passage by 12Z tomorrow may also affect the temperature. I predict there will have been the passage of either a warm front, cold front, occluded front, stationary front, or no front within 140 miles of the reporting station. Now if we go and click on the discussion of fronts, basically the criterion is that a front is within 140 miles of your reporting site. So an example of a front near Iowa, if you're reporting for or making a forecast for Des Moines, anything within this block here, this block, or this block will be within 140 miles of the reporting station. And you see examples here of cold fronts and warm fronts. Basically, the cold front is delineated by this blue line here with these triangles, and actually the air behind a cold front, okay, if the front's moving from left to right on your screen, the air behind the front is colder than the air ahead of the front. So this is the region ahead of the cold front, the region behind the cold front, and so as this front is moving from left to right, temperatures will begin to decrease. Now, with a warm front, the region ahead of the warm front is right here. The region behind the warm front is located where I'm showing the cursor, and this warm front moves from south to north, or from bottom to top. And so as this front begins to move past your area, temperatures will begin to increase. This is a low pressure area. We'll talk about that a little bit later. An example of a stationary front, this is a front that is not moving. It is stationary, and it's indicated by alternating triangles and these circles here, red circles, blue triangles. An example of an occluded front is shown here in this pinkish purplish type area, and it is an alternating actually triangle and circle all on the same side. This occluded front is also moving from left to right. So it gives you a little idea about fronts. Another parameter that you'll forecast for is advection. And you see here that you're forecasting for the presence or absence of advection and the type of advection. Recall that advection is a horizontal movement of air in this particular case. Well, if you want more information about temperature advection, just go to this link here. And what I would recommend that you do at this point is to pause the module for a few minutes and read through this particular area. So if you would pause at this point. Okay, let's pick up again. And the definition of advection is the horizontal transport of temperature by the wind. So you have temperature being moved by the wind, being moved north, south, east, or west. And for these particular forecasts that you're doing, we will say that significant advection will occur when at least a 1 degree Fahrenheit temperature change due to advection occurs in the 2 hours before 18Z. So for instance, the total change for 2 hours, 17 and 18Z is 1 degree Fahrenheit. We also do the same thing for 12Z. We'll look at 11 and 12Z. Now keep in mind, we've been talking about radiational cooling. That's when the infrared energy is leaving the Earth and going off into space. The surface begins to cool. That is not advection. That's radiational cooling. So when we're talking about temperature advection, it's typically located in the vicinity of a front. Okay? So we'll talk about those particular examples here in a moment. So an example of significant advection would correspond to about a 10 mile per hour wind blowing directly across isotherms. We have heard this term before. isotherms. These are our temperature lines that when we go to the University of Illinois website, we'll see that. In fact, let me just pause here a moment and let's take a look. We'll go back here a moment and actually take a look at the isotherms at the University of Illinois. And we're looking at surface here. So we'll click on this and we'll click on temperature contours here. And we see these lines of constant temperature. Everywhere along this line is 20 degrees Fahrenheit. This is what we call an isotherm. This is the 20 degree isotherm, a 25 degree isotherm. And so we see temperatures changing across Iowa. Northeast Iowa is below 20. Central Iowa is between 20 and 25. Southwestern Iowa is between 25 and 30. So we see the air to the southwest is warmer. Now, is this warmer air moving from Kansas into Iowa, or is this colder air moving from Wisconsin through Iowa down into Kansas? Well, let's check winds. So we'll go down here. And we'll look at surface observations. And we see that winds, let's say over Kansas City, we have a southwest wind here. Des Moines, a southerly wind. Out in Kansas, a southwest wind. Up into Minnesota, Minneapolis, a southwest wind. So the air is coming from the south-southwest. And so you would figure temperatures are going to warm. Now, do we have a 10-knot wind across Des Moines back down into Kansas City? No, it looks like we've got about a 5-knot wind. But let's get a little bit closer into the area to see. Again, we're forecasting for advection, significant advection. In this particular case, since the winds are from the south and southwest, we would expect warming to occur. And there you see Iowa there in the center, and you see 5-knot wind along the Iowa-Kansas border, Iowa-Nebraska border. All these winds here that I'm showing with the cursor are 5 knots. So these are weak winds. Warmer temperatures off to our southwest, and since the wind is coming from the south-southwest, we will bring in some of these warmer temperatures. But will it be considered significant warm air advection? Well, let's go back to our definition of what is temperature advection. We will define significant advection when we have a 10-mile-per-hour wind blowing directly across isotherms with a spacing of about 10 degrees Fahrenheit over a distance corresponding to the north-south dimension of Iowa. 42-hour period. Now, that looks it's probably a little confusing at this point, so let's look at one of these examples. Notice that we have a 10-degree temperature difference across from northern Iowa down to southern Iowa. If you go from north to south across Iowa, you see a 10-degree temperature change. You'll also notice the wind speeds. What direction are they from? They are from the north. You see the wind direction here. And the wind speed, 10 knots, or for our case, 10 miles per hour. And so we've got northerly winds, a 10-degree difference across the state of Iowa, 10 knots. We would define this as significant cold air advection. Again, here's the definition. A 10-mile-per-hour wind blowing directly across isotherms. Again, we'll go back to this example. These are isotherms, lines of equal temperature. 10 degrees here, 15, 20. And so again, we go back to that definition. A 10-mile-per-hour wind blowing directly across isotherms with about a 10-degree difference in temperatures across Iowa. This would be considered significant advection. Now, when we looked at the surface chart, we noticed, when we were back at the University of Illinois, we looked at the surface chart and we saw winds coming from the south, southwest. And they were blowing pretty much across isotherms, but they were only 5 miles per hour, so it's not considered significant advection. There's also some information here. There is a link here called Advection Help, and I'll just take you through some of this. You should spend some time going through this. Basically, for advection, we need to know the wind and the orientation of the isotherms. You have temperature of 80, 60, and 40. You have a southeasterly wind. The wind is coming from the southeast. It is bringing in warmer air. If you have winds over here from the northwest, it's bringing in this 40-degree colder air, so you would have cold air advection. But what if the winds are parallel to the temperature lines, the isotherms? The temperature is not changing, and so you would have no advection. So we have examples of warm advection, cold advection, and no advection. Well, what do you check? You check the one affected by warm air advection, cold air advection, not significantly affected by advection. Again, remember from the definition, we need a 1-degree change caused by advection over a 2-hour period, 11Z to 12Z, and 17Z to 18Z, depending upon which question you're answering. This would be a 10-knot wind blowing across a 10-degree change across Iowa, as per our previous example. Now you can actually do some math with this. You would take the winds, here's the formula here, you take the wind speed times the change in temperature. Okay? And so in this particular example we have the wind speed right here, 10 miles per hour times a change in temperature. Remember in the example it was 10-degree difference between northern Iowa and southern Iowa over a 200-mile distance. You do the math. 10 times 10 is 100 divided by 200. The units here cancel out, and so we're left with 0.5 degrees Fahrenheit per hour. So we're saying the temperature changes by 0.5 degrees Fahrenheit per hour in our example. Now, since we're doing it for 2 hours, we multiply by 2, and we come up with a 1 degree Fahrenheit change in a 2-hour period. So therefore, that would be considered significant advection. Here's some other examples. Let's say, for instance, now these are isotherms. We've got 25 degrees here, 30 here, and 35 down here. And we're saying basically there is a 10-degree change. Notice the wind direction here is from the north at 10. Okay, so we've got a 10-degree change. So we have cold air advection. Now, you notice I'm talking about a correction factor. I'll mention that here in just a moment. But for this particular example, you don't have to worry about it. So a 10-degree change with a 10-mile-per-hour wind gives us 100. In this particular example, there is a 20-degree change. The winds are from the south. So if you're sitting here where the cursor is at, with time, temperature will be increasing. So we call this warm air advection. This is an example of a 20-degree change with a 10-mile-per-hour wind. Now, notice right here, we have a 10-degree change here, 25 to 35. Notice the wind direction, though. It's out of the west. It's a due westerly wind. If you're sitting here, the winds are out of the west, the temperature is not going to change because you're sitting on an isotherm. the winds are not bringing in cold or warm air. You may have to pause the video here for a moment just to look at this example to get an idea of what's going on. So again, we've got a 10 mile per hour wind. However, there's no change in temperature as we go from left to right here. Now, this is this correction factor that I was mentioning a little bit earlier. Notice we've got a 20-degree change from 25 to 45. Notice, however, your winds are from the northwest. They're at an angle to these particular isotherms. In fact, it's a 45-degree angle. In a previous example, we had the winds directly out of the north. But in this angle, it's northwest, so we have to build in a correction factor. And so that correction factor would be 7 here. Now, this is probably a little more detailed than you want to get into. I mean, we're making forecasts. I don't want you to get this detailed in terms of trying to figure out what's going on in terms of the math. But I'm just trying to show you some examples here. I'm going to come back to some of this particular examples here in a few minutes. Now, here's a slide here. One of the things that you have to determine is wind speed and wind direction. Here you see a southerly wind, and this is for 12Z, and for 18Z you see a southerly wind at 5 knots. At 12Z, a southerly wind at 10 knots. And so at this point, you're trying to figure out whether you have advection. Now, the particular charts you're looking at here, this is a map for 12Z, and this is a map for 18Z. And you see temperatures across Iowa. It looks like this is 25 degrees over northern Iowa, 30 degrees over southern Iowa. So you have about a 5-degree change in temperature over Iowa with a 10 mile per hour wind. As you know, that's not going to be enough for significant advection. Same thing here. If you look, we have a southerly wind at 5 knots. It's 40 degrees over northern Iowa, 45 over central, and about 47, 48 over southern Iowa. We have about an 8-degree change over the state of Iowa and a 5-knot wind. Again, from our previous example, that's not considered significant advection. So really, you can just eyeball these with your general rule of thumb. Keep in mind, typically we want a 10-degree change over Iowa with at least a 10 mile per hour wind to forecast for significant advection. Here we have a 5 mile per hour wind, you see the barb there, and we only have an 8-degree change in temperature. Here we have a stronger wind, 10 degrees, but again, only a 7-degree change across Iowa, not the 10-degree change that we need. Okay, what you can do at this point, you can actually use one of the simulations that we have called Advection Sim. And if you click on Simulation, you can actually use Advection Sim to help you figure out if you're going to have significant advection. And so what I'm going to ask you to do is to scroll down here to the last applet, or this last, go ahead and click on it to activate. And so what I'd like to do at this point is to go ahead and set the different parameters. And so what you can do is, what you try to do is replicate the isotherm spacing here. So if we use that example, actually let's just go ahead and go back here a moment and see what is happening currently with temperature. So what I'm going to do is I'm going to go to Weather Products, and I'm going to go back to the University of Illinois, the surface. I'll look at the surface and see what the winds and temperatures are doing. So we'll go to University of Illinois here. We'll look at temperature contours. And we see across Iowa, let's see, we have 20, 25. So the actual temperature here is 15 back into Chicago, 20 over in Iowa. So the temperature here across northeastern Iowa is about 17 degrees where I have the cursor. It's between 15 and 20. It's closer to 20, so it's about 17. The temperature in southwestern Iowa is somewhere between 25 and 30. So we'll say about 27 and 17. So we have a 10-degree difference across Iowa. That's one of the things that we look at. Do we have a 10-degree difference? We'll also need to see what the wind directions are. So let's go ahead and pull up the wind direction. And we'll go to surface observations. Click on that. And we'll see that winds are out of the southwest, out of the south, southwest, at about 5 knots. And so let's go ahead and put those two items into Advection Sim. So again, we've got southwest winds, wind speeds 5 knots, and as we know, the temperature changes by 10 degrees across Iowa. We saw the temperatures in northeast Iowa at 17, and southwestern Iowa 27. So let's go back to our help menu for temperature advection. Click on the simulation, and again we'll go down to the last version of Advection Sim. So again, let's go ahead and pick our contour spacing. Our wind direction we know is southwest, so we set our direction to southwest. We can change the wind speed here. We know we've got a 5-knot wind speed. We're interested to see if there's going to be significant advection, so we can change the bar here. We're looking for 2 hours to determine if there's significant advection. Notice that here, according to this example, we've got a temperature of 22 and a temperature of 30, so there's about an 8-degree change across Iowa. In the example, or in the actual observations, there's a 10-degree difference, so we're pretty close there. So let's go ahead and run this. Notice that the initial temperature is 26. We've got a 5-knot wind, narrow spacing since we have almost a 10-degree change across Iowa. And let's go ahead and run this. So in a 2-hour span, we went from 26 and we stayed at 26. And we already had a good guess that we would not have significant warm air advection because the wind speed was simply too slow. It was simply too slow. Now, let's say, for instance, our actual wind speed was 10 knots. If we go ahead and increase this to 10, let's go ahead and run it and see if we have... There we go. We have a change from 26 to 27. We had a 1-degree change over 2 hours. So if there would have been 10-knot winds, we could have forecasted for significant advection. So I hope this module on fronts and advection has been helpful for you.